Okay, this work is about transfer learning in the context of Bayesian optimization, and it's work done jointly with Jenatton, Matthias Seeger, and Archambeau from Amazon Berlin. And it's mostly based on scalable hyperparameter transfer learning, which is a paper that recently appeared at NeurIPS. So consider the following problem. You have a deep neural network, and you want to tune the parameters so as to optimize some performance. For example, you want to minimize the test error. Now, the search space is quite large and diverse. You have the architecture choice, number of layers, number of units. You have the optimization parameters, so how to set the learning rate, momentum, and you also have the model complexity, so you can tune the regularization level. So the problem is that every time you want to know how well one of these hyperparameters perform, you need to train the neural network. So it's very expensive to know what is the performance associated to some hyperparameter. The two most typical approaches to achieve this are grid search or random search. So you typically propose...
Your aim is to train your neural network, but do you have a specific application in mind, or is it a general neural network?
It's a general neural network.
Okay,
so
it
it's
can be for anything, for imaging, for sailing?
It can be for image recognition, for example, or MNIST as typical, or any other application.
It will work in any case?
Yes, you need to have some general purpose way to tune your parameters, as long as you can specify a black box that drives you from hyperparameters to performance. And so what typically researchers do is proposing parameters at random or in a grid. The random strategy is slightly more efficient, because if you have a parameter which is not relevant, then you are not proposing multiple times the same irrelevant hyperparameter. The problem with these approaches is that essentially they are memoryless. So every hyperparameter that you already tried has no effect on the future hyperparameters that you might try. So they are sort of wasteful of resources, although they are very easily parallelizable. So what we like to do is to have a more principled approach to hyperparameter tuning, which is actually not memoryless. And a typical use case is transfer learning. So suppose you are tuning a SVM model, or a machine learning model, over a given data set. So you will have some loss function, loss surface that you're trying to minimize, and you start proposing hyperparameters, the gray dots. Then you're given a new data set, so you want to, again, you want to minimize the test error of the same model over these different data sets. So we expect the surface to be different. Finally, you're given a third task, a third data set. And so the question is, while the surface that you're trying to optimize is going to be different for this data set, is it actually possible to reuse what we learned from previous tasks? So is it possible to actually reuse the hyperparameters that we already tried for previous optimizations? And if we are able to do this, we are able to actually speed up the process much more, as long as there is some similarity between different tasks. So suppose you have some hyperparameter tuning system, and customers come with their algorithm that you want to tune. So customer 1 comes with a given data set and model, XGBoost. Customer 2, customer 3. Each one of these times, you want to find the best hyperparameters for that given problem. So essentially, you run some search, and you collect observations, x1, y1, for each given task, where x is the hyperparameter vector, and y is the performance, the test metric that you care about.
What is the test metric?
So the
do you want the customer to be happy? Do you want Amazon to be happy?
So the test metric usually is, for example, for MNIST, you are trying to minimize the test error. So throughout these examples, you can think of the test error as the test metric that you want to minimize. But again, it extends to any kind of metric that you would like to optimize somehow.
Okay, as long as it's differentiable, it can be.
Actually, I'm going to cover the kind of function that we need. It doesn't even have to be necessarily differentiable. And so it's interesting to ask if it's possible for customer T to actually leverage what was already done for customer 1 and actually reuse this pool of observations x1, y1 that we already collected for XGBoost on a different data set. So this is essentially a transfer learning question. We want to exploit evaluations from previous tasks. And we want to do this, in particular, in the absence of metadata. So typically, when you have a data set, you also have quite a lot of meta information that characterizes the data set. For example, you have the data set size, you have the class imbalance if you have a classification problem. So you have a lot of metadata that you might exploit. But of course, there might be privacy concerns if you want to transfer this metadata from one customer to another. So we want to be able to achieve this transfer only by looking at the evaluations themselves, so without looking at metadata. But of course, to be able to do this, we need to have some scalable model. We need to be able to use a very large number of evaluations that have been collected so far. So stepping back for a moment, let's frame this problem more formally. So we have a function f that we wish to optimize, and it's typically non-convex. And we want to do a multivariate optimization. So we have a number of parameters, which is p, typically of moderate size, so less than 20. And we want to minimize the function f, our black box. F is a black box in that it's very expensive to evaluate, and we have no closed form or gradients for f. And moreover, evaluating f can be a noisy process. So when you try one hyperparameter, you're not necessarily observing the true value of f. It might be corrupted by noise. So this is a challenging task, and f, in a nutshell, can be regarded as a black box. So going back to the first example, you have a deep neural network. F is the mapping from hyperparameters, so number of layers, number of units, to the test error. So you want to minimize the test error by trying different combinations of hyperparameters. And of course, this mapping f of x is very expensive. It's a black box, because every time you want to see what is the test error associated to some hyperparameters, then you need to run an entire training loop. So it's very expensive. And the only thing you can do is querying f at new points. To achieve this, we resort to Bayesian optimization, which is a principled, model-based approach to tackle this kind of problem. So we have our function f that we want to minimize. So the idea of Bayesian optimization is to place some model over f, some model that represents your current belief about f. And as you go along, you can update your knowledge about the model by updating the model as you observe more and more pairs, hyperparameters, and test error, for example. So until you run out of some budget, for example, time, you set a time limit, you pick a first candidate based on the current model about your black box, M, and based on your current candidate, C. And you select these new candidates so as to trade off exploration and exploitation, in the sense that you want to minimize f, so you want to pick a hyperparameter setting which is likely to give you a better optimum, but you also want to know how this function what this function looks like. So you want to pick candidates where you are most uncertain about your function, so you get a better idea of what it looks like. So once you have a new proposal, x, a new hyperparameter, vector x, then you collect the evaluation y. So for example, the test error. You train the neural network based on these hyperparameters x new, and you get y new. And this is the most expensive process. And finally, you can update your set of candidates C with this x new and y new pair. And based on this new set of candidates, you can update your belief about your model, M. So you update your model based on C. And then you update your budget. And you keep going as you are out of dollars or out of time. So what do researchers typically do? They place a Gaussian process model over F, over the black box F. And the Gaussian process is a particularly nice model because it models what a function looks like, f of x, in such a way that it's tractable. So observations yi are Gaussians with a given mean and covariance. So once you have fit your Gaussian process over your black box F, then you're able to know what is the predictive mean and variance at each point. So you have an idea what querying a new point will look like in terms of uncertainty and in terms of optimum. So based on the predictive mean and variance, you can pick a new candidate so as to balance exploitation and exploration. So as I mentioned, you want a point which is likely to give you a better optimum, but you also want to explore the areas of your posterior function where you have the largest uncertainty, so you can have a better model. So for example, you have queried f at 4 different points. X is the hyperparameter that you want to tune. Y is the performance, for example, the test error. Then, based on your Gaussian process model, you know that the posterior distribution looks like the one above. And you can use this to optimize some acquisition function. For example, in this case, the expected improvement, so as to balance exploration and exploitation. So you know that the best point to propose next is the one that optimizes this acquisition. Again, this acquisition is based on the posterior mean and variance of the Gaussian process above. But the goal of this work is actually to take this Bayesian optimization approach to a transfer learning setting. So we do not only look at one given black box, but we have a set of different black boxes, t different functions. And for each one of these functions, we have already run some hyperparameter tuning. So we have already collected pairs of hyperparameters and performance, x, t, y, t, for each one of those. Again, we may or may not have metadata associated to these datasets, and we want to optimize a given function f t0, so just one of those, but exploiting everything we learned about similar related tasks, similar related functions. Note that this is not a multi-objective problem in that we are only interested in one function at a time, but we are interested in doing this by leveraging what we learned about similar functions in the past. We do not want to optimize several metrics together at the same time. There has been quite a lot of previous work trying to achieve this. Gaussian processes, GPs, have been extended to a multitask setting so as to be able to model multiple tasks at the same time. There has been some heuristic that tries to look at tasks that are the most similar to the current one and then fits a Gaussian process only based on the current task and the most similar one. And then there are some ensemble-based approaches based on neural networks and GPs. But what is the problem with Gaussian process? The problem is that it doesn't scale well with the number of observations n. So when n, your number of candidates so far, is very large, then you have a cubical scaling in n. So it's not really straightforward, feasible to fit a Gaussian process if you have a huge amount of previously evaluated hyperparameters. So we need to move away from Gaussian processes to have something that scales better than n to the third. And this is why in this work we propose falling back to a simpler model, which is ABLR, Adaptive Bayesian Linear Regression. So the model is pretty straightforward. You take your observations y and you model them as independent Gaussians. W is the weight vector, beta is your noise parameter. And the weights, W, are also distributed as Gaussian random variables, where alpha is the scale parameter. X is our hyperparameter vector, and Y is our performance metric, for example. Note that we do not feed directly X into the model, but we first take a transformation phi of x. And this transformation is parameterized by z. So this is a very simple model in that it allows you to compute the predicted distribution. So if you have a new point x star, a new hyperparameter vector, then you have in closed form what is the distribution of the metric at that hyperparameter x star. So you know the distribution of y star is still a Gaussian with a known predicted mean and predicted variance. So how do we use this in a transfer learning context? Instead of having just one of these ABLR models, we have T of those, one for each task. So we have T conditionally independent ABLR models, each one with its own scale and noise parameters, alpha T and beta T. So what is shared across tasks is phi of z. So the mapping that learns representation for your tasks is the same across all different tasks. And phi, to be more concrete, could be, for example, an explicit feature set or random kitchen sinks, or what we look more into is we learn a neural network that maps hyperparameters to a d-dimensional representation. So phi will be parameterized by the weights of the neural network, z. And in this context, we have a multitask objective, which is given by the sum of the log likelihood for each given task. So again, the choice of phi is pretty crucial. We will explore neural networks to learn a representation for your input vector, or also random Fourier features. So you draw u and b from a Gaussian and from a uniform, and then you map x, your hyperparameter vector, using this transformation, phi of z. In the first case, z will be parameterized by all the weights of your neural network. In the second case, the only parameter that we need to learn is sigma, which is the inverse bandwidth of the RKS, random Fourier feature transformation. To give a clearer summary of ABLR, we have a model which looks like this. So you have, for example, 3 different tasks. Each one comes with its own hyperparameters and performance metric, x1, y1, x3, y3. Then all these tasks share the same phi z, the same feature mapping, in this case the neural network. But each one of those has its own specific ABLR layer at the end. So you have a Bayesian linear regression on top of a neural network, which is shared across all tasks. So how do we use this model in practice for inference? Again, we have alpha t and beta t, the scale and noise level for each task. And we also have z, the neural network weights, which are shared for all of them. We take an empirical base approach, and we marginalize out the weights for each Bayesian linear regression. So all we are left with are the alphas and betas, which are task-specific, and we have the weights of the neural network z that we need to learn. And we learn them by minimizing the negative sum of the negative log likelihoods for each task. Again, this is a very straightforward model compared to GPs. It's a much simpler model, and we have a posterior mean and variance at a new point x star. So it's really easy to use within Bayesian optimization to pick new candidates. And we also have a marginal likelihood, which is summed over different tasks. Now, what is interesting to point out is that in order to compute these quantities, we still need to invert a matrix, just like in Gaussian processes. But this matrix, KT, is now a d-dimensional matrix, while in Gaussian processes, it's a covariance matrix over all observations, so it's an n-dimensional matrix. So in practice, we need to invert a d-dimensional object, so this will scale as d to the third, as opposed to n to the third for Gaussian processes. So it's much easier to use this in large-scale settings. Another caveat is that in order to perform inference, we need to compute derivatives. of the marginal log likelihood with respect to the parameters that we are trying to optimize, so alphas and betas and z. And we also need to drive the optimization, we also need to have the derivatives, so the predictive mean and variance at each point with respect to the input. Note that this is not that straightforward because we have a Bayesian linear regression model on top of a deep neural network. So computing these derivatives is not necessarily easy. The neural network could be arbitrarily complex. So to do this, we leverage deep learning frameworks. In particular, we leverage MXNet, which allows us to just specify our target loss, the marginal log likelihood, and get these derivatives automatically by back-out auto-differentiation. Note that we also need to backpropagate derivatives through a Cholesky decomposition, which is possible because the backward operator for the Cholesky decomposition has been recently introduced into MXNet. And this allows us to use any feature map phi of z. In practice, what are the optimization properties of this algorithm? As I said, it doesn't scale cubically in the number of observations, but it scales cubically in the D, the feature space dimension. And typically, we will have T, a few tens of tasks, and we will have a number of points for each task, which is very large. To optimize these parameters, we use LBFGS to jointly learn all hyperparameters Z, alpha, and beta. And as we go along in the optimization, the convergence of LBFGS is pretty quick because it's warm started with the current state. So we are able to use LBFGS and still scale to a very large number of observations. Now, how does this model, ABLR, relate to what has been done, introduced already in the Bayesian optimization literature? So Gaussian processes are really the most widely used model in this setting, but it's not the only model. There has been a variant which is much more scalable than Gaussian processes, which are sparse Gaussian processes. The problem of sparse Gaussian processes is that they require you to pick a small number of inducing points to make inference tractable. The advantage is that it doesn't scale cubically in the number of observations, but it scales linearly in n and quadratically in the number of inducing points. The problem is that it's not really straightforward to use in a Bayesian optimization setting, as the predictive uncertainties cannot be very accurate, are not necessarily very accurate away from observations. There have been more recent variants of Gaussian processes, deep kernel learning, for example, which uses some approximation to make Gaussian processes scalable, and it's a valuable alternative to our ABLR approach. And then there are random forests and other neural network-based approaches. For example, Snoek et al., which is the first work that uses, instead of GPs, it uses Bayesian linear regression on top of a neural network, but only looks at a single task. And then there are fully Bayesian neural networks that have been used by Springenberg et al. In 2016. ABLR compares to this setting, this set of models, as it's in that it's very simple, conceptually very simple. It scales linearly in the number of observations, and it allows you to transfer knowledge across different tasks, even in the absence of metadata. The NGO is the existing model that uses a neural network on top of which there is a Bayesian linear regression, but it only looks at a single task. So we extend this setup to a multitask scenario. So this is how we use this model in practice. You have T different tasks. You want to optimize task number 2 based on all the observations that you acquired so far. And you have a shared feature net and a shared joint, a sum of log likelihoods that gives you your learning criterion row. Just a few words about how you could achieve transfer in a different way. So So far, we aim to achieve transfer by having this split multiple loss structure, so one Bayesian linear regression for each task. Another way to do this, if you have metadata, if you have context about datasets, could be to simply stack your metadata to your hyperparameter vector. So you have x1, xt, your hyperparameter vectors for each task, to which you stack your context. In this way, you can simply run a simple optimization by taking all previous observations with the context stacked together. So you have a fixed part of the input, which is the context, and the variable part, which is x, that you're trying to learn to optimize some test metric. And of course, you could combine this context idea to ABLR. So you could have ABLR with a different model for each task, together with the context or without context. So let's look at first at some simple experiments to demonstrate these properties of ABLR. So consider these three-dimensional quadratic functions of this form, where A, B, and C could be thought of as contextual information. So you draw A, B, C uniformly at random from 0.1 to 10. So in this way, drawing 30 different triplets of A, B, C, you generate 30 different tasks. So 30 different functions which are related to each other. And we aim to optimize one of these functions based on observations, 10 observations that have been acquired for the 29 other functions. So these are some first empirical results. On the left-hand side, we compare random search. So we propose hyperparameters at random, and we compare all these algorithms in terms of the best minimum found so far in the optimization at each iteration. So each iteration is, in theory, an expensive step, as it involves evaluating your black box at a new hyperparameter. As you can see, basically all methods based on Bayesian optimization outperform random search. So it's really useful to be able to leverage previous information instead of proceeding at random. But what is interesting to see is that ABLR is comparable to GPs. But as you introduce transfer into ABLR or into GP, you're able to converge to get to a better minimum much faster. So if you can warm start your optimization with previous related tasks, then you're able to converge much faster. On the right-hand side, we compare to alternative neural network-based approaches from Snoek et al. And Springenberg et al. Using full Bayesian neural network, this Bohemian method. But we observe that ABLR is able to converge competitively in the non-transfer case and much faster in the transfer learning case. And our conjecture is that not just relying on context, but relying on a specific multiple loss structure is able to model tasks much better, because you can adapt to the noise and scale level of each individual task. Of course, the GP performed competitively in this setting. However, we know that GPs do not scale well in the number of observations n. Here is a simple comparison of work log times as you increase the number of evaluated candidates. And of course, GPs become unfeasible as soon as you have more than a few hundreds or thousands of evaluations. On the right-hand side, we also compare different choices of the basis function, either a neural network or RKS, the random Fourier features. And of course, the random Fourier features gives you a much faster algorithm because you only have one hyperparameter, the bandwidth, to optimize, as opposed to the entire set of weights of the neural network. Now, looking at some more realistic example, we consider datasets from OpenML, which stores for each algorithm and dataset a very large number of hyperparameter and performance pairs. So we use this OpenML data to optimize an SVM model and an XGBoost model. So what we want to test in this experiment is whether if we warm start our optimization with other previously obtained observations from related tasks, first for SVM and then for XGBoost, we want to test whether we are able to actually converge faster. And note that in this setting we have a number of evaluations which is of the order of 10 to the 5. So of course we cannot use Gaussian processes to this end. We need to have a more scalable alternative. Here, similar to the previous example, we compare the best value observed so far. In this case, it is 1 minus the area under curve for our classification problem for a set of competing methods, competing algorithms. And as you can see, again, just like in the previous case, if you warm start your optimization based on what you observed from previous tasks, you're able to converge to an optimum much faster than if you simply ignore everything that was done for different data sets. So there is actually useful knowledge that can be extracted from a different data set when you're optimizing the same algorithm. And this is the case for both SVM and XGBoost. Finally, we look at a slightly orthogonal problem. So instead of looking at different tasks, we wanted to investigate whether it's possible to apply this ABLR idea in the context of multiple signals, where by signal, I mean that, for example, you're training a neural network to optimize the test error, but as you do so, of course, you need to train the neural network, so you also have the training error for free. And you might also have the training error at each epoch. You might also have the cost that it took, the computational time that it took to get to that test error. So you have a set of signals together with your main signal. And we want to check whether it's possible to actually transfer information across different signals. So it's slightly different from the multitask setting that we looked at so far. Again, for example, you want to tune a neural network for binary classification, and on top of the validation accuracy, you also have the training accuracy, or the CPU time. And the idea is that these side signals that basically come for free could be useful to actually learn a better joint representation for phi, the shared neural network across tasks. So you're able to map hyperparameters X to representation more efficiently. These are some experiments averaged over 5 different libSVM datasets. And again, basically all algorithms outperform random search. But what it's interesting to see is that if you consider ABLR and you jointly model multiple signals, for example, the training loss, the cost, or the training loss acquired at each epoch, you're able to actually converge faster. So it means that there is information which can indirectly be exploited to better learn a shared representation for all tasks. So there are, and this is an interesting idea because these signals are rarely exploited when you try to optimize your test metric. So to wrap this up, we looked at Bayesian optimization, which is an interesting model-based approach to automate somehow machine learning, in that it allows you to have hyperparameter-free algorithms and models. It can tune them in a clever way based on previous information. But we took this a step forward, and we wanted to see whether we can look at multiple tasks together and whether we can exploit information across different tasks. But to achieve this, we needed to have a more scalable model compared to Gaussian processes. So we developed ABLR, multiple ABLR, adaptive Bayesian linear regression, which allows you to actually scale linearly in the number of observations and successfully transfer knowledge across different tasks or signals. It's also interesting to see that thanks to deep learning libraries such as MXNet, we are able to perform exact empirical Bayesian inference in settings where it would not be straightforward otherwise, because we have to perform inference through an arbitrarily deep neural network. We have a Bayesian linear regression on top of a complex neural network model. So we need derivatives through this neural network model, which is not straightforward. So it's interesting to see how Bayesian modeling and deep learning could be combined together to perform efficient Bayesian optimization in the context of multiple tasks. Thank you.
Thank you very much for this talk. Are there any questions?
Thank you very much for the presentation. Maybe two questions. The first one is, how much is the acquisition function important? And when you have parameters that have very different dynamic ranges, for example, if you were to have the depth of a neural net versus the learning rate of the optimizer, all these things have very different dynamics. And so how does the GP framework handle this?
So that's a very good question. So one thing to note is that we mostly looked at different algorithms. We looked at the same algorithm trained on different data sets, so that the hyperparameter space is of fixed dimensionality P. And of course, it would be interesting to see how we could extend this in the case of different algorithms, for example, or in the case of algorithms which have a different hyperparameter space. So this is an interesting extension of this work. You also have, the previous question was the first one? So yeah, that's another good question. Throughout these experiments, we fixed the acquisition to the expected improvement so as to have a fair comparison, but it could be possible to simply take a different acquisition and use it together with ABLR. For example, you could use entropy-based acquisitions, which have been shown to give better convergence compared to the standard expected improvement. We mostly focused on the model rather than on the acquisition, but these two could be combined.
Thank you. Are there other questions? So if not, I think it's time. Oh, sorry.
I think that this question is also related to the question that Alexander asked. The necessity for this to work is to have the same features, the same feature functions.
Yes, so in this formulation, you need to have the same hyperparameter space, and that's why we looked at the same algorithm throughout different data sets, so that the hyperparameters are the same, but we have a different surface.
So if there are no further questions, I think it's time to thank all the speakers for today, and we're then to be ready for tomorrow's session.